Okay, hello everyone. Welcome to the CSP seminar this week. And we're pretty happy to have our speaker, Professor Stanley Chen, and also Dr. Nick Chimitt from the Purdue University leading us today. And so for this seminar talk, we will look into some very interesting topic about the computational imaging, as you have seen in the slides. And so just to give some introduction before we get the talk, but before we get started with the talk. So Professor Stanley Chen is the professor of the electrical and also computer engineering at Purdue University. He received his PhD from the UC San Diego, a very beautiful city, and also did a postdoc at Harvard between the 2012 and also 2014. He does many very great research in the computational imaging, especially for the photon-emitted imaging and also imaging through the atmospheric turbulence. So I think that's also the topic for today. And he's definitely the recipient received a lot of very impressive awards, including the 2022 the IEEE SPS Best Paper Award for the very well-known plug-and-play AEM paper. I think many people doing the optimization computational imaging, they all read that papers. And also the receiving the 2016 IEEE International Conference in Image Processing Best Paper Awards. And he's taking a lot of papers authors and also the co-authors. And for another speaker we have today, Dr. Nick Chimitt, also from the Purdue University. So he's currently a research scientist at Purdue University. He received his PhD from Purdue in 2023, last year, and currently working on the imaging through the turbulence. And he's the co-inventor and also the co-author for multiple books and also the authors relevant to these topics in the atmospheric turbulence. And he has also delivered the tutorials, the talks, and also organizing several workshops in this field. So that's very exciting to have both of them visiting us today in the UMich city and also give us the talk. So Stanley and Nick, feel free to take your turn.
Thank you, DJ. Thank you everyone for coming. It's my pleasure to come to Ann Arbor today. We just give you a little bit background. We have a pretty busy schedule today and tomorrow. We are going to Michigan State tomorrow for a PI meeting from 8 a.m. to 5 p.m. And then we got the invitation from Leah and we arranged. And thank you so much for accommodating our schedule so we can stop by here. And thank you for hosting us. We're going to talk about imaging through atmospheric turbulence. It's a journey. What we're going to do today is that we're going to split the talk into two halves. I'm going to introduce the topic, and then Nick will talk about the background and some groundwork that we've been doing in the past. And then we'll share with you more on the deep learning side and things that we've been working recently. Okay, so to get started, let me tell you the beginning of the journey, and let me find a way to remove that thing. Is that okay? Do I have the control, or do you? There should be some.
End it maybe first.
Stop sharing.
Yeah,
Maybe
sure.
do you want to do it?
Yeah, let's do that. Yeah. Let's do it. I think if I just end it for a second, come over here. Okay. I'll get rid of that too. Okay. Yeah. Let's do. I always forget where. I'm a fake Mac user. I just got it like a year ago, so I really don't know all of them. Okay. All right.
Okay.
Yeah.
Perfect. Okay. All right. So beginning of the journey. So it's a story, a short story, and that can sort of tell you why I'm working on this problem. So back in 2017, a sponsor in Ohio, they reached out to us and they say, at that time was assistant professor, and then they asked, hey, are you interested in this problem we've been working on for some time? And since you've been working on various ADMM algorithms, maybe you can try it. So I sort of okay, let's try it. And I recruited Nick, and at that time, poor assistant professor and a poor student jumped on this wagon, and then we produced something. And then after a couple of months, we realized we got this. Okay, it wasn't working at all. And there's a big reason because we are optimization by training. We do forward modeling, and it's not about our prior model. It's total variation is nothing wrong. Just that the forward model is not right. And so we are not able to deliver any good solution. So we go back and then to the books. And 7 years later, and we should feel proud, okay? We did a little bit of accomplishment. So a book is published on this topic. 2 tutorials are given in CBPR and ISIP on this topic. And I think the community is also using some of our work in their projects. So we feel pretty proud of ourselves of making this accomplishment, although there are lots of things for us to learn as well. So what we are trying to share with you is how do we get from 2017, the realization up to today, what are the things that we have been doing? And hopefully that can be inspiring to some of you. And then some lessons that we learn here, maybe some of the techniques that we learn here can be as useful to you as well. Okay, so this is the brief agenda of this lecture. So next we will talk about part 1 and part 2. What is atmospheric turbulence? So we need to explain that, okay? Then how do we simulate these effects? Basically, how we build a correct forward model. Once we have the forward model, then it will be our world, okay? Solving inverse problems, plugging in whatever priors we want, and then deep learning, embrace deep learning, okay? And part 4, if time permits, I will talk about wavefront estimation, okay? So that's our agenda. Okay, Nick, your time.
Hello, everyone. Yeah, it's cool to be here. I know I'm just kind of the tag along, okay? So I'm gonna try to keep my time to like 15 to 20 minutes, okay? And then you can have maximum Stanley time, okay? So that's like, that's my goal, okay? But maybe the first goal I should have in mind is to talk about what is turbulence, okay? So when I think of like imaging through atmospheric turbulence, I think of this kind of like mirage-like effect, okay? So if you're in West Lafayette, you set up a telescope, look at Saturn, you see this kind of look, okay? Or if you put some sort of poster with words on it about 500 meters away, you zoom in, you see this shaking effect. And what's going on is the index of refraction between the camera and the object is random, okay? And the reason that is because the way that the air mixes, so according to Van Gogh, okay, it mixes in this turbulent fashion. But I think maybe we'll take someone a bit more, I don't know, academics word for it, okay? And so actually Kolmogorov in 1941, and it is probably the Kolmogorov you're thinking of, okay? It's not some other guy. Really proposed the key statistical model for turbulence that is still used to this day. In fact, turbulence is basically divided into Kolmogorov turbulence and non-Kolmogorov turbulence. So you can sort of feel the impact of this model. And then a grad student of his basically combined his model and applied it to the indices of refraction of the air, and then slapped in Maxwell's equations, and then he sort of gave rise to this whole field of imaging through atmospheric turbulence. So really, the key thing to know is that it all comes down to the refractive index. So maybe you're kind of familiar with this concept, okay? If I were to put a pencil on a glass of water, I see this kind of dramatic bend pencil, right? And that's due to the, sort of relatively large change in the indices of refraction. For the atmosphere, those differences are really, really tiny, okay? And they're seriously about this small, this many zeros, and then like a 2 and a 1 and a 3, okay? It's seriously that small. So, but the way that the atmosphere is mixing, there's this non-uniformity about it, okay? And now, even in this room, this turbulent mixing is even happening right now, okay? Think about how much I've moved my hands in the last 3 minutes, okay? There's definitely turbulent mixing. So how come I don't look this way? Okay, it has to do with that scale of the numbers that I just showed you. It's 1.00000, so on, okay? It's simply just that the distance is just simply not enough to accumulate those atmospheric effects. So if I get a real nice camera with a real big aperture and I zoom in really far away, those things start to add up and accumulate. And eventually I get all of these little teeny tiny phase distortions that eventually give me this kind of look to an image, okay? So we're going to talk about how do we really model that, okay? So that's the key thing. Okay. So in order to understand this problem, the forward process, we basically need to understand 2 things. One is how does the wave propagate through the atmosphere? And the other is how does this impact an imaging system? Okay. So let's start with the camera thing first. Okay. So the way that we're going to model the camera is basically just a linear system. Okay. So there's an input, there's an impulse response, which I'll call the point spread function, and then there's the measurement. Okay. And really that's just about it. Now the key thing to know is how do you describe this impulse response, the point spread function? So it's this function right here, magnitude square of the Fourier transform of, and then some physical quantities that I'll describe, okay? So P of R, that's the pupil function, and it corresponds to just maybe what you think, like the pupil of your eye, okay? It's the entrance of your camera. And then phi of R, this is like a phase aberration. So for example, okay, so I wear glasses, okay? So if you have an astigmatism, you would put the astigmatism right there, okay, something like that. And if you're trying to focus in a camera, okay, and you have this defocus blur going on, you could sort of describe the defocus in this term, take the magnitude square Fourier transform, and the corresponding point spread function would be big or small, depending on the size of the defocus. So that's how a camera works, okay? That's the model we're going to take. So how to connect that to turbulence? Well, when the light propagates through the atmosphere, and I'll describe exactly what these things are in just a moment, it's, as I said earlier, it sort of accumulates these phase distortions. So you can think of turbulence, the point spread functions that come out of the system, as these sort of very complicated defocus terms. Okay, that's basically the idea. So what are these things that I've shown you, these flat 2D screens that I've shown you a couple times? Okay, so this is basically a discretization of the continuous volume that is the atmosphere in between. Okay, so it's mixing in a turbulent fashion. And then what I'm going to do is just, I mean, even theoretically, they do this too, by the way, okay? But I'm just going to pull out a few representative chunks, okay, of the atmosphere. And then say the brightness in each of these planes here correspond to the more index of a higher index of refraction. So if it's like 1.0005, and then a dark region is really 1.0001 So and they have this kind of look to them, okay, kind of a smoky. I always think of them as like smoky screens, because that's kind of what they look like to me. So how do we generate these phase screens? So this is where the turbulent model comes into play. Okay, so Kolmogorov basically tells us a particular power spectral density, and then he also says that the way that the index of refraction is distributed is a Gaussian random process. So I have a power spectral density and I have a Gaussian random process. So that means I can just pull samples from it all day long. Basically, the power spectral density parameterizes the whole entire distribution. Okay, so I can just pull samples from the power spectral density. Okay, so that's where the Kolmogorov part fits in. Okay, now I'd like to talk sort of like in a programmatic way. Okay, how would we use these phase screens? So let's say I generate like, I think 5 phase screens here. Okay, I just pull the samples from the power spectral density. And now I want to propagate waves through them. Okay, so I'm not going to so much talk about exactly what's the mathematical formulation of this wave propagation, but I'm just going to, again, just give you a programmatic view here. So what we do is we put a point source here. Okay, so you can think of it just as a little light bulb turning on at the red, green, or blue, something like that. Okay, and then I'm going to propagate it, wave propagation, to this first phase screen. Then I'll do a multiplication, e to the power j phase. Okay, so this phase screen. And then I'll go from here to the next phase screen. And I'll multiply by the next e to the power j phase, and then propagate again. So I propagate the next again, blah, 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 blah. Now, one thing I want to highlight is this is for every pixel in the image, I have to do this thing over and over. So I have to put a point source, propagate it all the way through sequentially. Put another point source, propagate it all the way through sequentially. Okay. And there's an important thing to know. If you know like much about, let's say, optics, okay, if you're familiar with angular spectrum propagation, okay, maybe you've heard that. If you don't, it's not a big deal if you haven't heard that, but that is how you're getting from one to the other. Okay, for those of you that don't know what that is, that corresponds to basically two 2D FFTs. Okay, one to propagate it, and then one to sort of get it back in the spatial domain. So every single time you do that propagation between phase screens, you have to take two-dimensional Fourier transforms. And I'll come back to how computationally expensively ridiculous, okay, that is in a moment, okay? But I mean, the computation is pretty crazy, okay? So, and then I'd also like to point out that, if you look at these points, say the red and the green one, they're propagating through similar sort of slices of the atmosphere. So if you imagine the cone, like propagating from this one and this one landing on the camera, there's really quite an overlap in that cone, okay? So what that sort of gives you is a spatial correlation between the effects. So that let's say the pieces of the atmosphere that they're accumulating are correlated in some fashion. Okay, so for Gaussian random process, there's a correlation between the phase rotations. Now this blue one is propagating through kind of a different slice. Okay, so it's kind of uncorrelated. So there's this notion of spatial correlation as well. That's a critical part of this problem. Okay, high level picture. Each point you propagate through the atmosphere, you get phase aberrations. Boom, boom, boom. That's like your complicated defocus. Okay. Then from each phase aberration, you can produce a point spread function. And then you use each point spread function in sort of just a linear systems fashion. Like you can think superposition, and you go from a clean input image to a simulated, or you could say observation output image, right? Okay, now let's talk about why that's so slow. Okay, let's just do a simple calculation. Okay, so 10, let's just say 10 phase screens. That's like a normal number people use. Okay, 256 squared pixels, and you need a pair of 2D FFTs per propagation. So it ends up being 10 times 2 times 256 to the power of 2D FFTs. Okay, so then you have to do a spatially varying convolution. So that's going to be even worse. Okay, this will take you. We did this one time. 156 years to generate a data set. Okay, so if I had any hope of graduating, okay, I'll be long dead by the time that we would generate that data set. Okay, so that would be pretty sad for me. Okay, so then this is sort of where we come in. Okay, so that's sort of the context, and also a bit to give you a feel about I guess what the field's about and how it works. Okay, so now let's talk about what we've done. Okay, so we sort of take like a diagnostic approach to this whole thing. Okay, we say like what's killing us. Okay, I mean, if you think of speed, what's really the problem here? It's the numerical wave propagation. Okay, so you can sort of dream, wouldn't it be nice if I could just pull samples of these phase aberrations right there without having to propagate them through. You see, that's sort of like the dream. Okay, because then you wouldn't have to do all that nonsense. Okay, so building block one. Okay, so in 1976, there's a guy, Robert Knoll, who writes a paper. Basically what he says is, okay, this is a Gaussian random process. Okay, I can do a basis expansion. I can write it as a sum of a set of polynomials. Each is the Zernike polynomials, and each coefficient is a Gaussian random variable. Okay, so then he basically asks, can I find the covariance matrix that characterizes the Gaussian random, I should say the basis coefficient vector, right, which is a Gaussian random vector. Well, in long story short, yeah, he finds some function. Okay, so now it's horribly ugly. Okay, but maybe the reason it's horribly ugly, it more has to do with these than anything else. Okay. Now I don't want to focus too much on that function. I'd rather focus on what's wrong with it for our purposes. Okay. So what's he missing? Remember I talked about how the cones overlap, and that gives you this spatial correlation. So what Knoll basically gave us in 1976 only applies to a single point. So what he's telling us is what's the distribution of this coefficient, basis coefficient vector. He's not telling us what's the distribution of the entire random process that characterizes the whole field of atmospheric distortions. So here's sort of the way you can think about it. Knoll tells us a Gaussian random vector distribution, but we want to know the distribution of a random vector field. So a whole entire collection of Gaussian random vectors. Okay. So anyways, Knoll gives us this, but we want this. Basically, we want flexibility in choosing two different points. So in 2020, I think we have like an approximate way of doing this. Okay. And later it turns out that's kind of a rough approximation. Okay. But in 2023, we have a paper. And so we actually are able to derive the sort of wave propagation distribution of the phase aberration, blah, 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 all that stuff. Okay. Some sort of very complicated function. And I'm hiding that what this Fij is from you. It basically takes a whole entire page to make what this Fij. It's pretty nasty. Okay. So if you thought this last one was pretty ugly, okay, this one's even worse. Okay. But anyway, so we're able to basically describe the statistics. Okay. So what that's going to do is just let us draw samples of the phase aberration right here. So we don't even have to propagate it through the phases. Okay, so we feel happy, right? Okay, but now we've done so much work, okay? You feel like, we've just solved it, okay? But then you go and sit down, you start to program it, and you go, I still have to do this spatially varying convolution. And in fact, it's a point spread function for every single pixel in the image. That's gonna really hurt, okay? So all this work, and it's still gonna be slow, okay? So then we want to do something else, okay? This is the final kind of component here, okay? So spatially varying, what I've been calling spatially varying convolution, it's really just a superposition inference, okay? So what we want to consider is, what if I could decompose my point spread function as a sum of a different basis, set of bases, just like null hat is Zerke polynomials, we want to use a different basis representation. Well, it turns out if you do this, and you let the coefficient represent the spatially varying part, and you want the basis polynomial to be invariant, and you just substitute this in, okay, you get some sort of expression. Basically, it says you can write a spatially varying convolution, you can approximate a spatially varying convolution as a weighted sum of invariant convolutions, okay? But I'd like to mention that this beta m is actually of the same dimension as j. Okay, so it's actually like this is almost, you can think of it as like an image, like a coefficient image. So you can't factor it out. Okay, then you might ask, well, okay, well, how do I find those betas? Now, sure, I could start at these and then form the point spread function, do a basic projection, but that's just going to be more Fourier transforms, okay? Because that's how they're related. So you might ask, is there a relationship I can find between alpha and beta? Okay, that would be really great if I could find it. Then I could basically do the whole entire simulation without taking a Fourier transform. That would be awesome. But it's highly unlikely that you find something like this analytically. Okay, so when we hear that kind of phrase, something very dirty comes to mind, okay, which is just let a network do it. Okay, so just generate a bunch of pairs of phase aberrations, point spread functions, compute their corresponding basis representation, basically coefficients, right? And then train a network to just do this, okay? And as it turns out, this works so good that we've never even bothered measuring the performance. Well, as far as like the error or anything like that, it seriously just works that good. It's like, it's just, when you see it work, you're like, yeah, okay, that works like perfectly. Okay, it's like, I don't know, it's pretty, oh, I'll give you another piece of information about this. So I did my PhD with Stanley too. I basically never learned how to use the server for training anything, because I seriously just trained this on my laptop, on my CPU in like 15 minutes. This is how small this ridiculous thing is, okay? It's like 2 layers and it's like 50 to 100 neurons per layer. It's like nothing, seriously, it's just about nothing. Okay, so I think I'm doing pretty good on time. So I'll try to wrap up here in just the next couple of minutes and let Stanley take over. So now we have this really complicated depiction. I don't want you to get too stressed about understanding exactly what everything is here, but I'd like to just show you. I basically told you everything in our simulator at a basic level, which is we derived the correlation kernels, we generate samples from them, we send them through the P2S transform, and we approximate a spatially varying convolution as basically a weighted sum of invariant convolutions. Now, you might ask, what's all this here? Doesn't matter, okay? But it's just a little trick you learn along the way. It's not that big of a deal, okay? But that's the basic simulator. So to give you sort of a timeline of all this stuff, our first simulator paper came out in 2020, optical engineering, and then this dirty neural network trick that I just showed you. Okay, that's ICCB. Okay, fitting. Okay, and then TCI, TSP, optical engineering, that kind of stuff. And this one unpublished, but so that's kind of the timeline of development. And then I guess I think I'll probably just leave you with this. So you might ask, okay, so what's the significance of this whole simulator I just told you about versus what other people do? Basically, it's 1,000 times faster. So if you think about 156 years or whatever that was, okay, divided by a bit more than 1,000, it's more than 1,000 times faster, okay, but divided by 1,000, basically, we can generate data like insanely fast. So the big problem we were trying to solve when we started making the simulator was we just need training data in order to make deep learning restoration models. Because there's no ground truth in turbulence. You can't just turn the turbulence off, so to speak, right? Kind of what you see is what you get. So the whole point was generate realistic data. And again, I'm not going to live 156 years. So there had to be some sort of speed up. Okay, so that was the idea. So, all right, so then I'm just gonna skip this next slide, not a big deal. And then, yeah, I'll hand it off to Stanley. So thank you. Oh, yeah, question. Yeah, absolutely.
Yeah, it looks like it starts with plane and you get propagation from the plane to the next phase.
Yeah,
and
correct.
so on.
Yep.
So I guess you're assuming the house and the airplane, you're interested in small compared to the distance. Like you're essentially thinking of it as a 2D scene.
That's an excellent point. Yes, we are. Yeah, you are thinking of it as a 2D scene.
Okay.
So say you wanted to model some sort of depth variation. Now, if it's just a couple meters, because we're also talking about imaging over maybe 500 or more meters. So if it's just a couple meters, not a big deal. But if you do want to do like a really, say, wide variance in depth, then you're gonna have to get a little bit more fancy. So we've talked about doing that kind of stuff before, but we've never, I don't know, ventured that. Yeah.
Version 4 can actually do it because when you have longer distance, the variations of depth will actually go into the CN square, which is a parameter about the turbulence, accumulated turbulence rate, right? So you can model that into the simulator, and then to simulate that, you need to know the branch depth profile. So that's usually the hard thing.
Yeah, I guess you're right. I guess that expression does do it. But I guess I just don't think about it because I never, yeah.
Just want to make sure.
Yeah, no, you're absolutely right. Yeah, definitely. All right,
Okay.
all you.
All right, so let me talk about the image restoration, which is the inverse problem parts. Okay. So these are two example images that we were able to generate, and they're both real images. On the left-hand side, you can see that the input is distorted by the real turbulence. And then the image on the right is the recovered image by some methods, okay? And you can see, we don't claim we are the state of the art, but it's one of those methods that you can find in the literature that is achieving this performance. Okay, so what is the inverse problem? Now you understand that the atmospheric turbulence is affecting the appearance of an image, right? Then think about a little bit more. It's the phase distortion to the image. And by phase distortion, there are typically two types of distortions. One is the pixel is going to move, okay, from one location to the other location. You call it random jittering in the old days. In the optics, they call it the tilt, random tilt of the pixel. The other one is the aberration, all kinds of blurring effect. So there are technically two things, right? One is the moving of the pixels. The other one is the blurring of the image. Back in 2010 and even earlier, in our community, image processing community, people started to look at this problem by tackling these two issues one by one. This is a paper by Pema Mileva. This is 2013 in PAMI. So I guess most of the papers in this community is around this theme. So it's just one example to illustrate. You have a sequence of frames, they're distorted. The first thing you want to do is to register, right? So to undo the random movement of the pixels. Then the second step is to, they call it the near diffraction limit reconstruction. That's basically de-blurring, okay? And then the final step is, the second step, that is more towards a special technique called the lucky imaging. Okay, that to me it can be really coupled with the last step is the de-blurring. Okay, the concept of lucky imaging is that I have a sequence of maybe 1,000 frames, and because the turbulence is a zero mean Gaussian process, so from time to time I might be lucky to have a spot that is turbulence free. So if I have an algorithm that can automatically identify that sweet spots across the volume, space-time volume, I can construct he called it the diffraction limited image, and that is invariant. Okay? Of course, this is a very difficult task, and we have different ways to manage that. But you go back to the main story, it will be blur and movement of pixels. Okay, if you only have blur, life is easy. We have all kinds of deconvolution methods. If it is only movement, you can run optical flow and find them out. The mix of the two makes the problem a lot harder. Okay. All right. So after keeping this in mind, we can talk about various solutions. And this is self-promotion of what we have done, but of course, you can imagine there are a lot of great work along this timeline here. So I'm going to focus on two papers, okay? A 2024 TCI paper and a 2024 CVPR paper. It's the publication day. It doesn't mean the development day. Nowadays, when you publish a work, you got rejected and rejected and rejected. So you can have a delay of 3-4 years. So that's just the outcome when it is published. Okay, so I will share with you two pieces of work. The first one is a transformer. Okay, it's a fancy thing. Okay. I think the principle of this transformer, you can ignore the diagram, just think about it. The whole pipeline is very similar to the 2013 and even earlier 2008, all this kind of work. It's the same principle. You have pixel movement, you have blur. You don't want to handle them all at once. Decouple them. Okay, so that's the principle. Now, why do we choose transformers? There are technical reasons. Transformers certainly is used in language processing, but one very interesting feature of transformer is that it has the attention mechanism. I assume many of you know that word, right? Attention mechanism. So in the context of image restoration, when you have the attention there, you can actually tell the kernels where to pay attention to. So in the old days, when we have convolutional network, you have one kernel that is applied to all the pixels uniformly. That works when you have a deblurring problem, especially invariant deblurring problem, because everyone is being distorted in the same way. For turbulence, remember this lucky imaging concept, right? You want to move around the image and find the good ones, right? And so this attention mechanism will say, okay, at this frame, at this pixel location, you should use this set of kernels. When you go to the other location, you should use the other set of kernels, right? So this will allow you to immediately tackle a lot harder problems. We use transformer not because everyone's using transformer, it's because we did some experiment, we found that it seems to be the right approach to tackle the problem we have in there. Now, what I'm going to show you is how do we decouple the problem. The first one is the registered pixels. Okay. Now, some of you may be aware of our paper on whether you want to blur the image first and then you move around the pixels, or you move around the pixels or blur the image, right? In terms of inverse problem, I would say the boundary is not that important. Okay, you just do whatever you want to get the thing done. Okay, so in this transformer approach, we choose to deal with the pixel displacement first because we think that it is an easier problem. Not necessarily it is the correct physics. It's just easier problem for us to deal with. And there are a lot of designs involved, which I think is not the right venue to talk about these designs. Okay, but then you can think about it's a multi-layer, multiple scales, bigger resolution, lower resolution, multiple scales, and then each scale you do some attention and then walk around in the temporal domain because this is pixel registration, right? So that's the first part. The second part is the blur removal. So we have another unit. This is the attention now, not in the time, but attention in the space. So you have a different design over here. Again, the details is not too important in my opinion, okay? The third piece of idea, which is quite interesting, and that sort of differentiates our restoration model versus the other restoration model is that we have, because we build a simulator, so we can run the simulator in whatever way we want. Meaning we want pixel displacement only, just turn on the knob. We want blur only, we turn on the other knob. We want this kind of aberration, we turn on those. We don't want this aberration, we turn on those. And most of the people, they don't know how to play with our simulator, right? So we know that. And so we can drive the learning process in a way that we want it to do. For example, in the first stage, when we're doing the pixel registration problem, don't inject any blur into your learning, right? Remove all the aberrations, just ask the network to learn how to deal with the pixel displacement. Then you can add the blur later on, and then you can ask the network to deal with the blur only, right? So having access to the simulator just immediately alleviates a lot of complexity, because if you're dealing with this turbulence, you know, okay, image, distorted image, ground truth image, okay, black box neural network training, you know it's very, very hard, okay, to do. But with the simulator, you can actually use the simulator in a way that you want it to be. To show you some images, so this is a view capture that we did several summers ago in West Lafayette, and these are the actual images that we capture, and I'm sure that you will say these words are not very recognizable, okay? And this is the real reconstructed results, and you can clearly see the words. And I think in 2022, we run a competition in CVPR asking participants to develop this kind of restoration network and see how well they can recognize the text. With, I think the best performer, they can achieve maybe 95 or 96% in terms of recognizing the text. And it's pretty good results. And then in this program, this is the IAPA program that we're going to present tomorrow in the PI meeting. This is a real data set collected by the government. The image showing you on the, is it a video? Yeah, we can look at the video. The video on the left is a real capture. I think it's done by Oak Ridge National Lab. And then the image that are showing on the video showing you on the right-hand side, that is with the recovered. So don't pay attention to the tree and the 7, but pay attention to the subject, right? Because the goal is to recognize the face of the subject. Okay, cool. Let me also talk about another network, and then.
Next question.
Oh, sure, of course.
Is the network you train here specific to a given distance and turbulence parameters or whatever? How generalized?
Yes. So when we train the network, of course we need to pick a range.
Yeah.
We pick a range, we call it a typical range, from 200 meters to maybe 1.5 kilometers.
Oh.
So we have this range, the whole range. Along this range, we also have several levels of turbulence. We say bad day, good day, so you can adjust the turbulence level. And inside, then you can have all kinds of parameters to match that goal. So in the training data set, we have the whole variety, the whole spectrum of conditions, and then we train the model. Yeah.
A single model for all of this.
A single model for all. Okay. Now, of course, when you go outside that range, will fail.
I see. Is that also the case for your testing samples? So is that testing samples you have from the real world also always falls into this?
Actually, we don't know what the real world is collected because it's government data sets. They never tell us. Yeah, so they do have some metadata, but we can share the experiences that the government labeled it is recorded, but it's terrible.
Oh, yeah.
The label is, yeah. So I think we are sort of semi-blind in those cases. Okay, I will have a little bit more comments after I talk about this, the other network. I will share with you a lot of lessons that we learned, failure lessons that we learned in this journey. So the other network is a improvement of the previous one. The previous one, it's running well, but then the biggest problem is the memory. So whenever you have a transformer, I guess many of you know, transformer requires a lot of memory. So especially for videos, that model we can handle maybe 20 frames, full resolution, 20 frames, and that's maximum. Go beyond that, your computer will just crash. Okay. This is another paper we published in this year's CVPR, although the date can be traced back a long time ago. It's a recurrent network. Okay. Without going into the details, just tell you the architecture is roughly the same, but then we replace some of the modules by the recurrent network. So here is still getting the motion, registering them, and then pixel registration, pull the features, and then have a module called the lucky imaging. So you have a little bit of fusion here, and then lastly you have the deblurring. Okay, so the structure, the philosophy is roughly the same. And I would say, from my experience, if you want to build a turbulence mitigation solution, it will more or less along this line, okay? Unless you train a black box, which one is not fun, two is it's very difficult to debug. Okay. Okay, so here are some examples, again, from the government data sets. You have input and you have output. Let me see which one is video. So this is a video. Okay. Right, so you can see the turbulence is removed quite significantly. The runtime of this model is much better. Memory-wise, it's much better because it's recurrent, it's much faster, much more lightweight than before. I'm not sure if I can show you some demo. So if you go to our website, you can see the difference between.
It might not be up. Are you showing that on the screen?
Yeah, I will just do it quickly. But then I need to play my mouse over here. Okay, I hope you guys can see it. Okay. So so just to show you some examples, you can go to the website, go to our project page. You can play around all these videos. Okay. But then now I have a trouble. I need to move this back. Okay. And then where is it? Haha. So here's the okay. All right. Okay. So some lessons learned. And it's sort of negative. Okay. Restoration does not always help. Okay, this is from our experience. I guess it's pretty sad to the image restoration community. If I say that.
Doesn't help facial recognition.
It doesn't help. It doesn't help facial recognition. Okay. There are a couple of reasons. Number one is that turbulence is a minor case in many of these practical scenarios. So you have, when the turbulence is too strong, it's hopeless. Turbulence too weak, you don't need us, right? And then you need to find the sweet spot to demonstrate your utility. So you can't force the problem to fit your method, right? You have a hammer, you cannot put nails. So this is a big lesson we learned. The other one is that good looking image doesn't mean it's better classification. That's almost always true in our experience. We have very good SSIM and PSNR. Even visually, it looks great. But then when you dump it to the classifier, it doesn't work. And certainly we can blame the classifier is not taking care of the restoration. You can blame everyone. You can blame the entire world, but it is what it is. The performance gain from restoration is not translated to downstream tasks. Number two is that diffusion models is even worse. I know I'm gonna hurt a lot of people's feeling, but because we have evidence from the evaluation from the government that diffusion models make things worse because you hallucinate too much. Across the entire BRIA program, which we're gonna meet tomorrow, a lot of methods, they have negative impacts in terms of recognition. So if your goal is to do the recognition themes as of today, okay, except for those turbulence cases, otherwise, just do it. Just do the recognition directly. Your network is big enough. Your network is so huge, it has capacity to deal with these distortions. The data is a lot more important than the network architecture. And in the limit of data, meaning that you don't have too much data, then physics will be your friend. So I would advocate more on the data. I would advocate more on the physics. Then I would advocate for a network design and compete with better numbers, because in the real world, the world is not as nice as you can imagine. Okay. All right. So I think we don't have time to go into the wavefront estimation. But let me go to the conclusion, and then we can take some time and have some interactions. Okay. Okay. But I still need to go through the slide. So if you see any slide you want me to stop, let me know. Okay. So Saturn adaptive optics. If you have money, you can solve some problems. Okay. Jeff, I showed you this in the Chicago workshop. Okay, it's the boom like this. Okay, this could be fun. Okay, so we want to train a the inverse of that network, and we asked a student to train it. He spent a couple of months over there, and then he got to this. Okay, basically it doesn't work, and there's a reason because the inversion of that model is phase retrieval. It's very hard. It's very hard phase retrieval. And so you have ambiguities here and there. And so we worked pretty hard. Nick and I found that the solution is to go away from the circle to triangle. Okay, so if you're interested in this topic, we can talk. This is more about phase retrieval. So if you know anything about phase retrieval, you face any difficulties on the ambiguities, non-unique solutions, we can share with you our experience. Okay. Okay, so we'll skip that. Okay, to just show you some results. As of today, we are able to recover the phase, basically the inverse of the problem, right? So in the forward model, you tell me the phase, I tell you the point spread function. I blur the image for you. Now I tell you the blur, you tell me what's going on in the phase. So that's the inverse, that's phase retrieval. As of today, with a little bit innovation in the shape of the aperture, we can do this inversion. Okay, so we skip that. All right, so just to conclude, and then we can have some interactions. I think there are a couple messages. Number one is I think turbulence is very fun. It's very fun. It's a problem. If you have been working on deconvolution or inverse problem for a while, I encourage you and invite you to take a look at turbulence. It's harder, but then you will sort of see the generalization of the tools that you have developed. The forward modeling is more important than the prior, and that is sort of interesting because you will be able to see things outside your comfort zone. So I will encourage you to try that. And I think turbulence, even though Nick and I have been working on turbulence for several years, I think a lot of lessons that we learned in turbulence is shaping us to tackle hard problems, including phase retrieval. If you asked me 7 years ago, would you do phase retrieval? No, it's convex optimization, and it's so hard. But now, after we learn the turbulence, we understand the physics, we understand the limitations. A lot of skills are transferable. So if you're looking at imaging through tissues, some of the lessons that we learn here, I strongly believe it may be applicable because there will be some scattering effects, but then you also have the phase effects. The Air Force, I came back from a conference. I know the Air Force, they're very interested in looking at the air pollution. They want to transmit the energy beams. You have a scattering effect, you have the atmosphere effect, so they want to know the behavior of the beam. I think we will be able to contribute some over there. So I think although this is a very specific topic, and I think that the general science and physics and tools that we develop here can be very generalizable, okay? Another lesson I want to share with you, and I think especially if you're a student, is some failure that we had, and then we summarize with this George picture, is that we always like deep learning, so do I, okay? We think deep learning is very, very powerful. But sometimes we are too naive to think that the deep learning can solve all the problems. And the scenario is like you ask George to be the conductor of the gigantic orchestra, okay? And of course, he's not able to understand all the instruments, and so he will mess up, okay? So it's just like your turbulence problem. Sure, you can train a big black box model to solve the problem, but number one, it's costly. Number two, it just fails all the time. What we have demonstrated is that you go to individual little box, right? And then the network that we have is 2-3 layers, trained in 15 minutes, small, and then you plug it back to the physics, and it works, right? So you use the learning to do the right task. It's just like asking George to just play one instrument and you ask him to just pick that instrument, do that thing. Don't ask the network to do things that it wasn't trained to handle. Okay. So I hope this lesson can be inspiring to you. And with that, I will stop here and take questions.
Thank you so much for the terrific talks for Nick and Stanley. This is so exciting. And then I think we do have like around 10 to 15 minutes for the questions. Any question from the audience? Also, we also have some attending from the room. I will check that.
Sure.
Okay, if not, I will cover some of them and do next time. Oh,
Yeah,
sorry.
yeah, please.
Yeah, that's all the explanation is a beautiful to explain why it works, how it works. The only thing my concern is about when you use a small number to predict urban beta. So do we know when it can succeed or when it will fail? For example, if we apply to the Air Force particular application, right? Suppose US trying to bait, right? So US Air Force use the technique, then the particular wrong one, right? So it's crash everything. So do we have some analysis to understand that? So when the network can predict what exactly we want and when it can fail or it will never.
Oh, yeah. So when will the network fail? There is operating range, right? So the network is designed to take the Zernike representation. So we have 36 Zernike coefficients, and then we have a distribution of these 36 Zernike coefficients that comes from the typical turbulence scenario, right? And so we divide the equation and we know how likely would your coefficient to take this value. So we sort of know that. Now, of course, in outside world, it can fall outside this range. But then I'm not too concerned, actually. My bigger concern is that the actual image degradation is not turbulence. Okay. So because the air is complicated. The air is very complicated, right? So you cannot assume that it is a phase only thing. Okay, there's always amplitude fluctuations. And we don't handle that. So if somebody takes our simulator and then simulate why it doesn't look like the scene, and we say, yeah, because you have fog on that day, and perhaps the wind is blowing in this direction, and we don't take into account of those, right? And like Jeff asked, what if I'm driving on the road and the road is converging, I'm driving on the desert, it's converging, why is the turbulence so uniform? Right, because we didn't know the distance, right? So a lot of limitations are on our simulator, but I would say if you allow me to dig a hole, draw a circle of the problem scope, within the problem scope, yeah, we are confident, but the real world is much larger than our circle, and we admit that we have limitations.
To know the weather or the temperature, something more information, then we can build a model more accurate.
It's always the cost versus the efficiency. So we label ourselves as the dirty computer scientists, electrical engineers that want to get the network trained. And we never claim we can replace the Air Force atmospheric experts because we're not there. Okay, so if they need to spend millions of dollars building that equipment, how can our stupid simulator beat them, right? So we got to understand the difference. Yes.
So in the end, I'm not sure I know whether your final forward model is linear or not. There is this MLP in the middle of it, but I think the MLP is describing only some coefficients of the point spread function, not of the image seen itself. Is that right? So it is linear at the end of the day. Is that right?
If you assume that the forward model is just that PSF, then certainly it's linear.
The space variance.
Even space variance is linear, right? If you go back to the phase space, no. So that's a Fourier magnitude square. Right. So if the optimization variable is in the phase, then we are not.
Oh, right. Yes, I meant for the first part. Yeah. Okay.
Right. But it's differentiable.
It's like the system, it's like you think the input image, the clean input image, and then the output degraded, That's the one.
That's linear operation.
And so,
That's
in fact, because you can think incoherent imaging, I guess like non-coherent, is linear in intensity. So
assume
our simulators follow
up
that.
to the lens approximations.
Well, correct, yeah.
So, of course, normally we ask this question about whether it's linear when we're thinking about using that forward model in reconstruction, but if I understood correctly, you're actually not doing what I would call, traditional model-based reconstruction. You're using that forward model to train a network to do the inverse problem, right? So you actually are never, the fact that it's linear hardly matters to you for your reconstruction methods. The fact that it's efficient matters a lot, so you can do lots of training.
That's correct.
Understand that?
That's excellent. Yes, yeah.
Interesting.
The
Okay.
hard part is not the linearity actually. The hard part is the randomness.
Yeah, okay.
Right. So if it's yeah. Yes.
I had a question
Mhm.
on how do you use diffusion models for classification? Yeah, so based on my understanding, so the method proposed is to first use diffusion models to do the image restoration and use the restored image to do the downstream classification. However, in the diffusion literature, it's not the most effective way to do that. So there are a way that you train the conditional diffusion model and then use the conditional score, you can do a zero-shot classification. And or you can extract the intermediate representation in the middle, like certain layers of diffusion models and use that for classification. Yeah, and most reports, like those are results for classification of downstream paths. So my question is like, what is you mentioned that diffusion model does not work here in classification, but I'm just curious, like, what is the method that's not working?
Yeah, so that is a paper by Ramachalapa. That's a state of the art image restoration. And so in there, I forget which venue it was, and then they show very impressive results. Okay. And then on their training data set and on their testing data set, they actually show state of the art performance. But then when we evaluate the methods on the government data sets, not we did it, but the Oak Ridge National Lab, it's a third party. They did an evaluation. They show that, so they have a curve. They show how many cases can that model behave and how can it perform well, and it was lower. So that's expected value. If you don't do, you just do blind guess, it's this curve, and then they are below. So I didn't have the time to dig into the exact details, but I can share with you that the images look excellent. It's the state of the art. Okay. On some testing cases, they beat everyone. On some other testing cases that are not following the training data, then the generalization seems to drop quite significantly. So as to why is it overfitting? Could be. Anything goes wrong, maybe, but I'm just sharing you that it's not working. It's not working. Yeah. So perhaps in a year or two, there will be a new model that can work better. Yeah. Yeah. Exactly. That we need to look into.
Just to follow up on that question, I wonder, like, state of art, is that based on the matrix or the PSNR, is that aim for the image restoration?
Yeah, so the recognition. So recognition, you have standardized data sets.
Okay, I see. So
Right.
it's the state of art on the face recognition matrix.
That's right. And in many cases, where do you get the turbulence data? Eventually, you use the same simulator to do the training and testing. So there is a unfairness in many cases. Then when you go outside this simulation regime, they go to the real world, then it's a different competition. So then the robustness will become an issue.
And also, like, what kind of standard way people will use for building like the face recognition model, because that could also have a different way to do the face recognition, right?
Mhm.
Also, if you are using like the learning-based model, it also rely on what kind of the training data you're
Mhm.
train the face recognition.
Mhm.
Is there any like some standard benchmarks or standard model people are using after you apply all this kind of the image restoration algorithms and then use that model to do the downstream task?
Yeah, this question is completely outside my expertise, and I need to ask Xiaoming from MSU to teach me how to do that. But basically, they have standardized the data sets for training and for testing. And there are a few pretty well-known techniques as the baseline. And so, for example, in the Michigan State, our team, we have the ADA phase. So that is sort of the backbone of the classification. And then they have evaluated on all kinds of standard benchmarks. And they have multiple scores. Now, what the scores are, I don't, of course, it's beyond me. But then they have multiple scores, then they report that performance. Now we have the restoration to put in front of them. Then they will do the fine tuning and see how the performance goes.
Oh, I see. So you're also you're fine-tuning on the face recognition.
That's right. That's right. If you don't fine tune it, then of course you just recognize the wrong face.
Yeah.
Yeah.
Sorry, to teach lab now.
Oh, okay.
Okay. Sorry for that.
No worries.
Okay, thank you so much.
All right. Thank you.
Yeah.
Thank you. Thank you.
Okay, so we only have 1 hour reserved for the CSP seminar this week.
I'll meet them, I guess so, I didn't know.
Yes, yes, I will check with Christy. Yes.
Oh, yeah.
Sorry, I'm just stop the recording.
Oh, sure, yeah, no, do whatever.